Welcome to this day 2 of the ML Ops Interactive Conference dedicated to understanding the best practice, methodologies, and principles of effective machine learning. My name is Nadia, and I'm a machine learning engineer at Wave, and I'm honored to be here today and to have the opportunity to introduce some of our amazing speakers. Before starting, I would like to remind you all that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speakers on your behalf after the presentation. So let's start. Our speakers for the session are Maximo Gurmendez and Javier Buquet. Maximo holds a master's degree in computer science and AI from Northern East University, where he attended as a Fulbright scholar. As a chief engineer at Montevideo Labs, he leads data science engineering project for complex systems in large US companies. He is an expert in big data technology and co-author of the popular book Mastering Machine Learning on AWS. Additionally, Maximo is a computer science professor at the University of Montevideo, and he is director of its Data Science for Business program. Javier holds a degree in computer science from ORT University in Montevideo. And since 2015, he has working with Montevideo Labs as a senior data engineer for large big data projects. He has helped top tech companies to architect their Spark applications, leading many successful projects from design and implementation to deployment. He is also an advocate of clean code as a central paradigm for development. Please join me in welcoming Maximo Gurmendez and Javier Buquet.
Thank you so much, Nadia, for your introduction. Good morning, everyone. It's a real privilege to participate in this great conference. My name is Maximo Javier. I'm here with Javier Buquet from Montevideo Labs. At Montevideo Labs, we worked with top US tech companies, helping them build smart data products with a quality focus always in mind. Today, we would like to share our know-how regarding the development of smart data products, starting from prototypes. We will argue why sometimes notebooks may not be enough when it comes to building proper software products at a given scale. Notebooks are a great tool for building prototypes and have drastically changed the way data scientists and engineers share ideas and collaborate. However, when it comes to building robust products, there are some limitations, and at times we might be tempted to overuse them. We will define what we call a smart data product and go through a list of typical mistakes that we could go through while moving from prototype to production. Javier will present a demo on how to take a notebook, break it apart into an Apache Spark software artifact, as an example. Finally, we'll share some takeaways from all the concepts discussed. So what is a smart data product? For starters, it's a product. It must serve a purpose to users and must have high quality standards. We're assuming that you're creating a system that makes decisions based on data, leveraging ML, AI, or data science. That is, in essence, a smart data product for us. Let's look at a few easy pitfalls that we've witnessed in the past when building such products, especially when we start from a prototype. Let me say that many things I'll mention may seem very obvious, yet I'm sure that many in the audience have experienced at least one of these issues. So the issue number one is to assume that assumptions on future data will remain the same in the future. Oftentimes, a data scientist presents a new strategy through a notebook, makes a presentation to a group of people about how a particular model, a particular data method might help the business in some way. It might forecast better, it might prevent users from leaving the company, it might pick the right price. Whatever those decisions are, they typically start with a prototype and some data set used to validate the methodology. When we build a product, we must cater for variable change. We should challenge the assumptions which are true at the moment designing the methodology. It's common to blindly take those algorithms to production, and we forget about the underlying assumptions that made the data model valid or useful at that time. Again, it may seem obvious, but it happens. Sometimes we just don't cater for the necessary model refreshes and how we need to mutate our models over time to allow for the new underlying assumptions on the data. Issue number 2 is to have data scientists and engineers do their own thing independently. Typically, engineers focus on stability of the system, the use of design patterns to make sure that modules are testable, cohesive, decoupled. Engineers are interested in performance from the point of view of low latency, high throughput, no concurrency issues, and that we're using the cloud in the most efficient way. On the other hand, data scientists focus more on iterative experimentation and successful prototypes. If these prototypes are good, then it's usually a very good outcome for data scientists. They're interested in performance, but mainly about model accuracy or business metrics. Oftentimes, some of these objectives are at conflict. For example, it's hard to perform a quick iteration in production for an A/B test if we need to ensure that models being served are truly threat safe, don't have memory leaks, don't cause garbage collection issues, etc. At the same time, chances are that those models that better perform in terms of accuracy may require a large memory footprint and are prone to creating other performance problems, typically latency. So the best for us is to have teams in which engineers and data scientists collaborate. If both profiles feel a sense of collaborative accomplishment and ownership, then chances are you will create exceptional products because you've worked together to explore all the trade-offs that make sense for the business. It's easy to assign blame when the culture is not right. When an issue happens, data scientists could say, the model worked perfectly on the data. Engineers will say that things might have worked on an experiment, but live data is showing otherwise. Team spirit here is key, and we believe it's possible. In fact, we've done it a ton of times. Issue number 3 is about metrics. We need metrics on our applications to ensure that models are still behaving the right way. As you can see in the diagram, those statisticians in the room might realize it's a Simpson's paradox. Oftentimes, we might be under the illusion that our models are behaving the way we intended to. But sometimes we're looking at the wrong metric. Good metrics are about business KPIs. And a good metric is sensitive to the most relevant aspects in which the model can go wrong. We might be tempted to use metrics that we, data scientists, understand very well, like area under the curve, ROC, precision recall, etc. However, ultimately, we want our models to improve the user experience. Better live metrics can show that we're doing the right thing, we're making the right final decisions. A/B test metrics, for example, are very useful because they prove that our ML is working better than a good, well-understood alternative strategy. User acceptance testing is also important as they help uncover unintuitive or confusing aspects of data products. In the past, we've faced a number of issues with very good models that don't play well when it's part of a user interface, for example. A sales prediction model in which they show a drop in sales when expanding to a greater region might be accurate based on the testing data, but might be incorrect or at least unintuitive to the user. Adding a unit test, for example, that checks for isotonic behavior might help catch this issue and prevent regressions. It's important to invest in maintenance of metrics. Metrics need to be maintained alongside with core code so that changes in one imply changes in the other. I've seen many cases in which metrics are not maintained and they become useless, which is very dangerous as our product now lies in the dark. Issue number 4 is about underestimating the importance of data dependencies. The models we build are based on data. And data is a result of several upstream transformations and ETL jobs. Many times, those transformations suffer modifications and improvements. We need to make sure that all those upstream modifications don't affect the assumptions present on our training jobs. We need to make sure that as the new data becomes available, new models can leverage the new data without breaking the system in production. For this reason, data streams or data sets need to be versioned and decoupled so that our models can read from the data that has the right set of assumptions. We can augment the data separately, version it accordingly, and later on deploy new models that leverages this new data. Meanwhile, models using the previous data version can still run unaffected. Javier will show a great example of this during the demo. The next issue is not to incorporate data science artifact as part of the continuous integration and continuous development, or CI/CD. Imagine the data scientist works on a notebook, runs a test, and through that notebook sends that model straight to production. That's very agile, and many times it works. However, we've effectively broken the continuous integration and continuous development chain. There's a reason why we have integration tests. There's a reason why we invest in all this infrastructure. It's about quality. Our code needs to be reliable and aware of the effects of data science-based artifact at a holistic level. The pitfall number 6 is about not investing in local integration and debugging. A lot of time is invested by engineers and data scientists to troubleshoot when things go wrong. So any upfront investment that we can make in this regard may definitely result in overall better productivity. Javier will show in the demo how this can be achieved in Spark. Though it's not always possible to have a complex and large system running on your laptop, oftentimes, if we decouple the modules the right way and achieve some sort of end-to-end integration, it's typically very useful. Even if the system runs at a very reduced scale, it can help validate plumbing issues and shed light on some inconsistencies. The next issue I want to talk about is not having proper environmental and experimental hooks. If modules are well designed, then any change in behavior that is determined by the environment it runs should be parameterized. Otherwise, it becomes very hard to ensure that products can run on our laptop staging environments as well as in production. Additionally, good software products allow for hooks and configuration knobs that allow researchers to test new ideas in production, inject little models such as A/B test with much lower risk. This also increases the ROI of the whole process as we promote only to production the research ideas that have proven to be successful in controlled live experiments. Next pitfall may seem obvious, yet it has happened. We need to be careful when running A/B tests. We need to make sure that we just don't hash the users and make a given set of users always be the guinea pigs and make them unhappy users. Additionally, we need to make sure not to abuse of running too many overlapping experiments and extract incorrect conclusions due to the effect of one experiment on the other. Next issue happens when we are so enthused about the potential benefits of AI and ML about a problem, and our confidence is so strong that we just go ahead and start engineering the product right away without doing a prototype and validate the method works. This might be okay at times, but normally we learn a lot from prototypes. We learn the unknowns, the things we didn't think about before. Knowing these aspects upfront typically allow us to design better systems. Finally, it's also very tempting to make the prototype the spec of the product instead of documenting the intended behavior. Engineers often need to reverse engineer the assumptions and possibly get the requirements incorrectly. Prototypes may skip some of the details which aren't important in a proof of concept, but may be very relevant when the product is launched in the wild. So Javier, having discussed all of these issues, how do we go about taking, for example, research artifact and moving it to production?
Yeah, thanks, Maximo. So in this demo, the idea is to walk you through some of the concepts that Maximo introduced and show you how to go from a prototype in a Jupyter notebook to a quality software product that still enables and encourages experimentation. The prototype that we will be starting from is borrowed from this Mastering Machine Learning on AWS book that Maximo co-wrote with Saket Mengel, a colleague of us. In this book, there is a chapter about recommendation systems, and it is backed by a cool example of how you can train your recommenders. For this, they use a public dataset from Pinterest that contains pictures of users in attractions, and each picture is considered to be a recorded visit from that user to that attraction. The recommender then can use all these recorded visits to find out for a given user what other attractions should be recommended. Together with the book, Maximo and Sackett created a Jupyter notebook in which they show how to load the raw data, prepare it as needed, and visualize it, and then proceed to train a Spark alternating least square model. As you can see, they then use this model to perform a few predictions and display them. It is not visible here, but they also show how to train a similar model from the same dataset using Amazon's SageMaker instead of the Spark algorithm. Of course, this works, and it's also very useful for iterating on different ideas quickly. But at Montevideo Labs, we strongly believe that high-quality software products should be built using proper software engineering tools, such as Git for the version control, or an IDE for development, or a continuous integration server. And as you may know, these are not very compatible with notebooks. As a first step to go from a prototype in a notebook to a production system, we suggest that you create a Git repository and set up a nice development environment that encourages good practices such as automated testing, peer reviewing, and local debugging. So in this case, we created a Scala project in IntelliJ. We do prefer Scala for our production code, but the concepts that we will present in this demo should apply perfectly well to any other language of your choice, such as Python. Using a dependency manager will also be very beneficial, not only for keeping track of your dependencies and which versions you are choosing, but also when you want to replicate your environment somewhere else, such as a CI server or another developer's computer. In our case, we are using Maven. So the number one key to developing highly maintainable software is to break down your solution into smaller and more cohesive components that can then be composed and reused. We do suggest that you break up your pipelines into smaller sub-pipelines that can run and evolve independently, and then you can figure out how to synchronize their inputs and their outputs. For this system, we decided to have three major components. The first component is the ETL, which basically takes care of loading the system's data in a form that is useful for some other of the components. In this case, we will be performing ETL on two different feeds, the visits, which can be seen as our facts table, and the attractions, which can be seen as our dimensions table. The second component in the solution is the trainer, which uses the loaded feeds to train any kind of recommendation systems model that can be used later for serving recommendations. And the last, but obviously not least important component in our system will be dedicated to serving recommendations using previously trained models. Ideally, this component exposes a service which receives a user ID and returns a collection of recommended attractions for the user using different ML models and supporting measurable A/B tests. Ideally, each of these should be treated as a very independent software component. In our case, we decided that they should be implemented as different Scala packages within one same project, but they could as well be different modules or different repositories. And they could even be implemented in different languages, as long as they comply with the predefined contracts. This will be very important for the maintainability of your system, making it easier to test, as well as allowing each component to be maintained by different engineers or even teams. In a common package, we can include any definition and utility to be easily reused by the other components. Of course, these independent components need to be composed and hence need to have some kind of synchronization mechanism for their inputs and their outputs. For solving this, we developed a very simple feeds framework which provides a way to communicate completely decoupled components by allowing a producer to put a new feed in the feed, a new update in the feed, and a consumer to retrieve the latest update in the feed following an implicit contract. We also included a very simple implementation of this feed, which relies on a file system for writing and reading the updates. Ideally, our implementation of the feeds should support keeping a history of the updates that were added to it, even if we will always be reading the latest update, as this will improve the auditability of our system. In our case, we are using directories in the file system here that are named after the current timestamp at the moment in which the update was written. This way, it is very easy to identify the latest update later on when retrieving it. These feeds are very easy to configure. In this case, for the visits feed, we just need to specify that we want to use the file feed implementation with a Buquet serialization and provide a relative path in the file system root in which we want to store the feed. An important thing to note here is that we are including a version identifier in that path. And this is a way to enable a better flexibility for introducing breaking changes in the feed producer without instantly breaking any active consumer, which is very handy, as Maximo mentioned in the slides. It is also very important that you make your environment configurable such that one same software artifact can behave differently depending on the configuration of the environment in which it is running. This is handy for turning a debug mode on and off, or for configuring the root path in the file system for your feeds. As you can see, we provide a default implementation of this trait that relies on environmental properties, which is useful for production or staging environments. But we also support programmatically forcing a configuration, which is in turn useful for automated testing, as we will show. Internally, the different components are very simple and straightforward for now. In the case of the ETL, we have defined two different loaders, one for the visits and one for the attractions. We added one implementation for each loader that reads its input from the same Pinterest data that is used in the notebook. The loader just delegates first to a reader and then to a transformer. We suggest that you keep these classes and units as cohesive and as small as possible to improve the testability of your code. As every component is supposed to run independently, we included a driver program in each. In this case, the driver is very simple. It first loads the visits and then puts that in the visits feed, and then does the exact same thing for the attractions. The training driver instead retrieves the latest update in the visits feed and uses that as the training data for the Spark ALS algorithm. The trained model is then put in the corresponding feed to be picked up by the serving component. The usage of the ALS algorithm is very similar to what is done in the notebook. The one thing that we improved is that we are setting a deterministic seed, which is something that we recommend to do anytime that you are generating random numbers, so that you get deterministic and reproducible results. In our serving component, in turn, we included an implementation of the recommender service that uses a previously trained Spark ALS model to perform predictions. As you might know, Spark models require that we create a data frame and then Spark will create a prediction for each record in it. In our case, this is not very convenient as we only want to do a prediction for a single user. And creating a data frame is expensive in terms of latency and not very neat in terms of code. You can watch last year's Spark Summit presentation in which Maximo and I presented an extension of Spark that we developed for supporting row-level predictions in a Spark-agnostic environment. And this is something very useful when your service has a low latency requirement. In order to support measurable A/B tests, we also included a very convenient decoration of the service that allows us to have different implementations coexisting in one same service instance, in a way that we can deterministically decide which one to use for each request. In this implementation, every time that we serve a recommendation, we compute a hash of the user ID and a salt to determine to which recommender the user should be exposed. It is important that this same hash can be calculated in an offline environment so that it is possible to attribute the results. We also recommend that you append a salt to the user ID so that you are not always exposing the exact same audience to your experiments, which is something that we have seen happening, as Maximo mentioned in the slides again. In our serving driver, we are setting up an experiment that will expose 50% of the audience to an ALS recommender using a previously trained model, and another 50% to a quite dummy recommender that always recommends the same attractions. In this case, we are recommending to leave anything that you're doing and go watch the ML Labs conference because it's so cool. In terms of testing, we not only structured our code in a way that makes it easy to add valuable unit tests, but also we have the ability to write very complete and automated integration tests. I'm starting to run the integration test, which will run all the components locally. And of course, this is very easy to integrate with a CI server. In this case, we are running the three components decoupled, and then we are asserting that all the supported feeds, such as the ETL visits, the ETL attractions, and the training model, are all populated in the file system. I will also show you in our target directory that the feeds. Sorry, it's not in the test classes. We will see when the integration test completes that the feeds framework is taking care of populating the feeds in the same way, or in a way that resembles the exact same way in which this will work in production. You can see here that we have our feeds framework, and we have all the updates for our version attractions. We also have the updates for our version visits, and also we have the update for our version model, which is a serialization of the Spark model. You can also see here that our testing framework accepts this run as successful, which of course is something that we could integrate with our continuous integration pipeline and add a very reliable check that we can run every time that we want to integrate a change in our code. So now that we have created these cohesive components that can run independently and be synchronized using feeds, we have a lot of flexibility for defining the architecture in which we want to deploy the product. The image shows the three components that write to and read from the feeds, which belong in a production environment that could perfectly be the cloud. There is also a research environment, which interacts with the feeds to do offline analysis and inject live experiments. Of course, the data scientists doing the research can also leverage the well-tested classes and utilities developed by engineers. This cloud could be fully deployed in one single server, with the feeds being stored in its local file system. We could as well take a more serverless approach, in which each component runs in its own container and uses an external file system for the feeds, which will give us great flexibility for scaling the different components as needed. For example, we could auto-scale an HTTP server for our serving component depending on its load. And we could use cluster of computers to do distributed ETL or training. Also, if we are working with big data, we could also think of implementing our feeds on top of a distributed file system, or even on top of Amazon's S3 or Glue. After an algorithm developed in research is proved to be successful through live experiments, it can then be incorporated into the corresponding production components by engineers. We have made this code available in our GitHub account, so please feel free to take a closer look to it and let us know any comments or questions that you may have.
Thank you, Javier. That was great. In terms of takeaways, we've been, drawing conclusions as we explored the different issues. So I guess the main takeaway is the obvious is often not as obvious, or we don't always do the obvious. So that is, to me, the main takeaway. Also work together in teams, data scientists and data engineers, measure all the time, decouple and integrate, run as locally, debug as much as possible, and be smart about the use of time, which is often the most expensive resource. With this, would like to thank you and are happy to take any questions.
Thank you so much for the presentation. So we had like some issues to see the code. So it was really too small. We couldn't read. So a lot of people ask if you can share the code. If you have the GitHub link, share it in the chat. This will help people when they get the recording to kind of go through again your explanation.
You can put back the...
Yeah, sure.
Thank you so much. Okay, so the link is in the chat. Everyone can access it. Okay, we don't have any other question. So let's give people some other minute. People says they cannot access the GitHub link you provide them.
Yes, that could be. In any case, when we end the session, what I'll do is I'll check that and let you know. I'm not sure if I can post in the session afterwards as a comment, maybe.
Yeah. Maybe it's a permissions issue, but we'll make sure that that link works that Javier provided.
Okay, maybe you cannot post it here in the chat of the event because we'll close somehow after, but you can for sure post it in the event chat, the general one. You can maybe introduce yourself and say, I'm Javier, this is the link. And yeah, so
of course, and anyone interested, please reach out to us. We have open profiles in the app, so just reach out to us and we can happy to share or troubleshoot any issues. Yeah.
Awesome. Thank you. I have a question though. So just come out. Why do you decide to use Scala?
Yes. So basically we do prefer Scala for our production code, and we also use Python extensively, but mainly for ad hoc analysis and stuff. And we prefer Scala for production on the one hand because we are using Apache Spark a lot, and Apache Spark is written in Scala, and that gives us a very easy way or a very easy API to integrate with Spark. So that's the main reason. And the other reason is that so we come from a Java background, and Scala is very similar to that. It's very similar to teach people, new people, Scala if they come from Java. So that's another thing. And in comparison with Python, we prefer our strongly typed and nice type system that Scala provides, and we think that it's more robust when shipping some code to production, and it's easy to have high quality if you have those types. So we do prefer the flexibility of Python for ad hoc analysis, but for production code, we use Scala for those reasons.
Thank you so much, Javier, for your answer. So I do have another question. In training, how do you measure the performance of the model?
Okay, so we didn't do in this case, but usually what we would do is we could extend you could do it while training or you could do it separately, but we would have an evaluation component after the training. And that evaluation component, what it would do is it would produce any kind of metrics that we want on the model. For example, the ones that Maximo commented, like the area under the curve, the ROC, those kind of things. And with that, we could decide if a model is valid or not to be shipped. Another thing that we usually do is that we have that as a separate component, a couple component that is able to, so if we are training multiple different algorithms, we are able to evaluate each and every of those. We are able to evaluate each and every of those in a different component and then pick what is the best model. So we will just do that in the training component if it makes sense, or in a separate component that can evaluate many different algorithms or many different models and pick up which one is the best to be shipped to the serving component.
Thank you so much. Another question, slowly they are coming up. What are your further thoughts on strategies to bring data scientists and engineers close together?
Yes, in our experience, in order to truly work together, you must be together, right? You must scrum together. Typically, we attend, the different plannings together. Both at data scientists and engineers, they make trade-offs, they make decisions together, right? To make sure that the culture is one in which the success of the product is seen as a success of both teams, and not one or the other. That is really important. It's really about leadership, and it's really about, if you put people together, and people like to solve challenges and people like to work in teams, it doesn't matter if they're a data scientist or they're an engineer, they will always work well in teams. That's our experience.
Okay, thank you. So it seems there are no other questions, but I do have a question. So
okay.
Seeing that I'm working with Spark 2 mostly, do you prefer to include your model and pre-processing together in a Spark pipeline, or maybe separate the two steps? And why you have that preference?
Yeah. We have this discussion lots of times. I think the answer is a second, but I leave Javier answer that question.
Yeah, so I would say it depends on the kind of processing. In this case, for example, we had some of the processing in the ETL, and that's cool because it allows you, as we said, to implement the ETL, maybe using some different framework if you don't want to use Spark for that. So you can have at a couple preparation of the data, which is actually also makes the outputs reusable for many training instances. For example, if you are always training with the same data, but you will want to train different algorithms, you can just do the preparation once, put that in the feeds, and then have many trainers pick up the latest update of that feed. And that's cool. On the other hand, anything or any preparation, and we have some in the trainer, which is very specific to the algorithm that we are training, we prefer to do that in the training stage and put it closer to the model, because we don't want to have a different component have very implicitly tied to the trainer components. Instead, in the ETL, we just do the general processing, and then in the training for each specific algorithm, we do the specific preparation of the data that the technical requirements need.
Yeah, and also when it comes to research, having data sets as useful as possible is one aspect to consider. In one extreme, you only have just the very raw data. Nothing is derived. There's no feature encoding done on the data, and data scientists can work through the data, but they need to redo a lot of the stuff that will need to be done anyway. On the other extreme, the data that becomes available in the data lake is too confusing because it has, one hot encoded features, and there's normalized columns there, and it might be very, very. First, it might be more expensive to store if we're talking about big data data sets, and secondly, it might be confusing for using that. So, like Javier said, any transformation that is very specific to the model most likely belongs in the pipeline, in the Spark pipeline, right? Whereas features or transformations that could be useful for analysis, could leverage the data scientists' analytic work, then there's no harm in adding it to that intermediate layer of pre-processed code.
That makes sense, perfectly sense. Thank you so much. Meanwhile, we got 2 other questions. So since you mentioned in the starting, do you create prototype from Jupyter Notebook?
Yes, we do. We showed that example from the book, but also that's something that we do in the industry too. Use Jupyter Notebooks, use Python, use pandas for that. So our data scientists love pandas. When it is more like big data and we want to use Spark, we probably would use, if we are using Scala or maybe Python too, we are trying to use Zeppelin, and we do have some utilities for running that on AWS, which is another notebook server there. And then there's the AWS notebooks, also the EMR notebooks, which some of the data scientists that we have worked with use, but that's not too widely used. And I think that's also Jupyter too. So in the end, we do use Jupyter, but when we do Scala, we sometimes prefer Zeppelin.
Yes, I can confirm that the EMR notebook or Jupyter notebook, I'm using it. Perfect. Okay, so we have the last question. By metrics, did you mean production operation metrics or model business metrics?
Both, obviously, but yes, it's a good question. The operational metrics, production metrics, they are very important to witness the health of the systems, right? And typically we add alerts when those metrics that are way easier to understand than sometimes the business metrics, and alarms and monitoring tools on such production operational metrics are very, very important, and we need to make sure that those are healthy. The more tricky ones are the business metrics, because things might naturally vary in the business. We can see trends go up and down. We can witness seasonality. We can realize the model sometimes doesn't make a huge difference. Sometimes the model just makes a tiny difference. That tiny difference often is important to the business, but in terms of the signal, that tiny difference is not easy to measure, or it's not easy to interpret. So I would focus especially on those business metrics, because they are the ones that are more challenging to get right. The operational metrics are more well understood and sometimes are easier to design.
Awesome. So that was the last question. So thank you so much to both of you. It was really an interesting presentation. I'm glad I had the honor to introduce you. So yep, enjoy the rest of the conference, and thank you again. Bye.
Thank you so much, Nadia.
Yeah,
thanks everyone.